Thanks for joining me. Today is Wednesday, December 4th, 2024. Sorry about those who are listening that it was garbled. Um, and thanks everybody for helping us with the Thanksgiving sale. So that seemed to go well, and that's really because everybody's support. So we all appreciate that. So today, I wanted to go over the paper that Gerald Pollack wrote called "Do We Breathe Oxygen?" And I had mentioned this paper a few months ago, and it was a paper that had been written by my friend Gerald Pollack, who I'm sure most of you know. And I was asked to peer review it, and because of that, it wasn't published yet, so I couldn't go into detail. I just gave a few hints of what it was about. And then today, somebody sent me the paper, not today, this week, sorry. And so that means it has been published. So now it's in the public domain. So now I can talk about it freely. And there's a few things about this paper. One is I think it's a great exercise in how to think logically, rationally, and scientifically. So that makes it worth going over. And the other thing is, I think it's of huge importance. Um, it's it's one of those things that we have a misconception about, and the misconception, I think you'll see, is easily shown to people who are willing to think. And then the repercussions of this misconception become clear, and then the strategy that actually can help people have better lives, I think, emerges out of clearing up the misconception. So it's similar to a whole lot of other things. You know, if you have the misconception there's a virus, you end up doing a whole lot of things which end up not helping you and, in fact, hurting you. And when you realize that's not why you got sick, you can do things that actually help you, and your life becomes better and freer and less fearful. And it's similar here. Once you understand what it is that we breathe for, that's not the right way to say it, why we breathe, what is it we're getting from breathing, then a whole bunch of avenues open up for you. Also want to say before I start, this may seem a little, I don't know what the word, maybe tedious, or because I'm going to read a lot of the paper actually. But this is going to be something that I think we're going to use in our curriculum and as a teaching tool to really go over this subject. So I'm hoping to spend the whole hour and really do a thorough look at this subject in this paper. And that's why I'm going to do it so thoroughly and carefully. And hopefully it's not too boring or, in fact, interesting. And the final thing I want to say is there are a few things that let's say, I don't know that I would say I disagree with, but I would say I would put them differently. I can also understand some of these things. I have a suspicion, although I don't know for sure, that Gerald actually knows these things and wouldn't be surprised to hear me say this. But it was easier, and in the forum of an academic paper, it's easier to speak in the language he did. And so it's not a huge deal, but I am going to point out some different ways of looking at it along the way. But again, it's not a big deal. Okay, with that introduction, let me share the paper. And we're going to link to the paper, so anybody who wants to find it themselves. But here it is. You can see Elsevier is the publisher, Medical Hypotheses. It's available at Science Direct. Here's the journal homepage there. Research article, single author, Gerald Pollack. Is it oxygen or electrons that our respiratory system delivers? So there's a few things here. So this is a little bit different than do we breathe oxygen? So he's asking the question, what is it that the respiratory system delivers to our bodies, to our blood, to our tissues that we collect from the air? It's similar to, is it oxygen that we're extracting from the air? So this is the way that he puts it. The other thing I want to mention about the title is, as probably a lot of people have heard me say, I don't think that the evidence is there that electrons actually exist. In fact, I think there's good evidence that they don't exist. And so if there's no, and I don't really want to get into the whole reason why I think that. There's some experiments that they use to claim that there are particles, like if you put certain current in a magnetic field, certain of that you'll get a deflection of the current. And they claim that if all there were waves, that wouldn't happen, that waves don't get deflected in a magnetic field. Therefore, there has to be some particle, some physical, thing, which they then call an electron, which is the thing that's traveling and creating the current. But I would contend, and I'm certainly not the only one, that that's not the only thing that could be deflected in a magnetic field. And so when you talk about electrons, you're getting into atomism and the whole atomic theory. And you have to realize that many of the luminaries in physics have actually said things like, if you looked in an atom, you'd never see an electron. So I'm going to use the word, is it electron, is it oxygen, or a charge? You could say a negative charge, although that's interesting. I don't know that there is a negative charge. There's different kinds of charges, and we call them positive and negative, but they're just different charges. So is it that what we're getting from the air a charge instead of the word electron? But you'll see this word electron, and again, I don't think it's a huge deal. Okay, so let's go to the introduction and say, questioning whether we breathe oxygen must surely seem bizarre, for oxygen deprivation quickly leads to suffocation followed by death. Could there be any question? And that's a great way to start, because it gets into the idea of, like, this is so-called settled science. Of course we breathe oxygen. Isn't that the whole reason we breathe? And if you don't have enough oxygen, then you die, and everybody knows that. And that's why they put you on oxygen in the hospital, so that you don't die, and that your heart is better, and blah, blah, blah. And we've all heard that. We've all learned it. All doctors know that. But we're going to find out whether that's really the case, as with so many things in our world. Yet certain enigmas emerge from the widely held mechanism of respiration, which are rarely addressed. And he's going to consider some of them. I go on to suggest a variant by which those enigmas resolve in a natural way. And the variant involves the central role of electrons, or I would say charge. For sure, oxygen is critical for life, but I raise the question whether it is oxygen itself, what is the critical agent, or electrons extracted from oxygen. Now, that's a very important paragraph. And again, this is extremely well-conceived and well-written article, in my opinion, because it's not the claim is not that oxygen, or what we refer to as oxygen in the air, is not important. The issue that is being addressed, is it the oxygen gas itself that passes from the air into our bodies, into our blood, or into our red blood cells? That's the question, not whether there's something about oxygen that is important. So one really has to differentiate these questions. We're not saying there's no role for oxygen. We're asking the question, is it the oxygen that gets absorbed or passed from the air into our bodies. So he begins by citing an issue that is not commonly considered in dealing with respiration, the breathing of fish at extreme depths. Oxygen is in short supply, yet the fish manage to survive. If vertebrate life requires oxygen, how do these fish make it? This paradox is relevant, so I'll deal with it later. For now, he's going to focus on people. So then he talks about the inspiration, expiration, inhaling, exhaling. During inspiration, we draw in atmospheric gases, that's the air, comprising not just oxygen, 21%, these are commonly given figures, but also nitrogen, 78%. There's also argon and some other trace gases. Now, interestingly, these gases don't make it past our lungs. Only oxygen manages apparently to pass from the alveoli, those are the little bubbles in our lung or air sacs, to the capillaries that envelop them, and they'll show you the figure. Nitrogen does not pass, nor does argon. Hence, whatever mechanism supposedly facilitates the passage of oxygen to the cardiovascular blood must somehow block the other atmospheric gases. So the process appears to be selective. Now, again, having been in medicine and gone to medical school and residency, nobody ever talked about that. These are like questions that nobody asks, and therefore nobody answers. So oxygen is not the only thing in air. And so if it's a simple diffusion of oxygen from the air into our blood, into our red blood cells, why don't the other gases also simply diffuse in? But they don't. And nobody asks that question, and Gerald appropriately starts asking the question. There's also gases that are noxious, like so-called halogens or poisonous gases, fluorine, chloride, presumably exert their toxic effect on body tissues, which implies they must pass through the alveolar membrane to the blood. Yet both molecules are substantially larger than nitrogen, which can't pass. The size is evidently not the determining factor in the passage from alveolar to blood. There appears to exist a complex selective paradigm. Certain noxious gases pass, oxygen passes, but other atmospheric gases, including the most abundant one, nitrogen, don't. Clearly, the inspiration mechanism is less simple than we thought. Now, we can fully rationalize the expiration process. That's the exhaling. Expired gas is presumed to contain carbon dioxide. As an end product of metabolism, that gas is considered to follow the reverse course of inspiration, passing from the tissues to the blood. Thus, CO2 is yet another gas to be added to the mix of those that apparently do manage to pass from the lung to the blood, notwithstanding the molecule's hefty size. The mix of molecules that do or don't pass raises the obvious question of why is this? Or how does the gas pass through any continuous membrane? Okay, not sure I have to read all of this, but let me just present the paradox that he's talking about. So clearly we can measure there's nitrogen in the blood, there's oxygen in the blood, there's argon in the blood, and other gases. We know that the nitrogen, for example, doesn't pass from the air into our red blood cells or into our blood, but the oxygen does. At least we think that the carbon dioxide goes the reverse way from the blood to the air. And if this was all based on size, then it doesn't make sense because the nitrogen and the carbon dioxide are bigger molecules, we're told, than oxygen. And so how do you keep a bigger molecule out and let a smaller molecule in if it was all simple diffusion through of the gas through the membranes? This is the same problem that I've talked about in getting the mRNA out of the nucleus. How do you get the mRNA out of the nucleus and keep the hydrogen ions from going in and out? What kind of hole lets something that's a million times bigger in out, but something that's a million times smaller doesn't let it get in? Or how do you have a door that lets elephants out but also keeps the mosquitoes out? The answer is you don't, which means the whole thing falls apart, and that can't be the way that this works. So then he says, by the force of Brownian motion, which is random motion, it's thought to go through these membrane barriers. On the other hand, gases such as oxygen form bubbles in liquid, shifting the question to how a bubble could diffuse through a continuous membrane. And there you see a picture of the air in and out and the oxygen going through three different membranes. So we have the alveolar membrane, the lung sac membrane, and then you have the blood vessel, the capillary membrane, and then you have the red blood cell membrane. So allegedly, this oxygen is traversing all three of these membranes by random diffusion. And here he's saying, even though it's a bubble, and so it's not just a gas, it's a bubble. How do you get a bubble through these membranes? And the same thing in reverse. How do you get the carbon dioxide from the red blood cell through three different membranes into the sac to be breathed out? And particularly when you factor in the fact that smaller things can't do that. So already we have a huge problem here, which he lays out. So he says, well, one possible mechanism is the opening of the pores. Since every balloon-like alveoli expands, expansion could open membrane pores, allowing oxygen to pass. But then the problem is, why doesn't the nitrogen pass as well, since it's smaller and 4 times more prevalent and should be going through the concentration gradient into the red blood cells, but it doesn't. So that can't be the case. And then he says there's a possible rescue. Some sources argue that notwithstanding its larger mass, oxygen volume may be ever so slightly smaller than nitrogen. He gives a reference, making its passage easier, which is why we breathe mainly oxygen. But the problem with that argument is that the volume of the two molecules are at least roughly comparable. They're next to each other on the periodic table, and they should be more or less the same rate, and we should breathe both. And further, a deeper inspiration, breathing deeply that opens these pores, would favor the struggling nitrogen. Yet even with deep breathing, we don't see any passage of nitrogen, so that theory doesn't seem to hold any water. So here's another possible argument for that. Another rescue option circumvents all these gas-based considerations. Since the alveolar membrane is a complex cellular system containing water, one could envision the dissolution of oxygen in the membrane's water. Through such dissolution, molecular oxygen could theoretically pass through the alveolar membrane to the capillaries. The problem is quantitative. In other words, the numbers, the solubility of oxygen in water is so low that we'd be perpetually struggling to breathe. So this option can't be right either. In other words, the ability of oxygen to dissolve in water is so low that it would cut off, it would make it impossible to get enough oxygen through breathing if this was the mechanism. So this cannot be the solution to the problem. So he says no obvious answer in this. So here's another issue that he gets into. To capture as much oxygen as possible, the blood ought to surround each alveoli as a continuous sheath, like a glove enveloping a hand. but it doesn't. The capillaries that surround the alveoli are separated. In most species, they are quantitatively sparse. Total capillary surface area enveloping each alveolus is estimated to be as the same order of magnitude as the surface area of the alveolus itself. While this measure might seem at first generous, it is not. Only a small fraction of the vessel circumference intersects with the alveolar surface. Hence, only a modest fraction of alveolar oxygen should make it into the capillaries, the rest wastefully diffusing beyond. A curious situation when nature might be expected to maximize oxygen transfer. In other words, the capillaries are not arranged in the proper way with the alveoli to maximize the diffusion through surface area and just random Brownian motion. And so that doesn't make any sense either. And so we have another reason why this can't be true. The third issue is what he calls capillary diameter, which basically is that the capillaries are way too big. Capillaries are way too small compared to the red blood cells. And in other words, the red blood cells are way too big, and so they have to squeeze through the capillaries, making the motion of the red blood cells through the capillaries way more difficult than it otherwise should be. And so you have to squeeze the red blood cells against the capillaries, which seems like a horribly wasteful and ridiculous way to organize this system. Like, why wouldn't the capillaries, the tubes, be bigger than the red blood cells so that the red blood cells could easily pass through and then pick up the oxygen? Rather, they're too big, the red blood cells, and have to squish against the walls of the capillaries, which seems to be a energetically wasteful way to go. Okay, so those are basically the problems with the current system. Just to summarize, how is it that the oxygen, which is bigger than the nitrogen doesn't get absorbed and the oxygen does? What kind of a hole or pore or diffusion system could that possibly be? And even the CO2 is even bigger. So that's one. The other is the arrangement of the capillaries around the alveoli, which makes no sense as far as optimizing diffusion. And the third is that the capillaries are too big compared to the red blood cells, which seems like a wasteful use of energy to squeeze these red blood cells through these way too small capillaries. So those are the problems. And so then he goes on to the hypothesis. And so what is a way to reconcile these issues? So he's going to suggest that it's not oxygen gas that our bodies require. That is, we don't breathe the oxygen gas, but electrons, or as I said, charge drawn from the oxygen. That is, no gas flows from the alveoli to the capillaries, only a charge extracted from the oxygen gas. We must recognize that the oxygen molecule is highly charged or electronegative, one of the most electronegative elements in the periodic table. That means it has a strong tendency to accumulate electrons or a charge. Well, that's interesting. Whether any tendency exists to give up these electrons in the right circumstance is less clear. Conceivably, some of these electrons could be drawn off by positioning a positive charge close enough. When opposite charges lodge near one another, electrostatic attraction can be of an impressive magnitude. Any such positively charged entity could thus serve as a receptacle for the oxygen's electrons or negative charge. And if that positive entity happened to lie within a capillary, then it could transport that charge or those electrons directly to the tissues downstream where it's needed. Hence, drawing the charge or the electrons from even the most electronegative substance would be plausible. Recognizing the ultimate need for electrons in tissue metabolism, we could envision the electrons transferred from the oxygen to the red blood cells, then delivered downstream to the relevant sites in the tissue in such a way the electrons could be delivered directly to the tissue absent any intermediate step. And basically what he's saying is, so what does the oxygen have? Well, clearly it's the one of the best, if not the best, carrier of this so-called electron or electronegative charge. And if we have something that's electropositive, which we will find out in a minute is hemoglobin, then you can have a mechanism where the hemoglobin attracts this negative charge from the oxygen, and as you'll see, this starts to make sense of the squeezing of the red blood cells in the capillaries to facilitate this transfer of charge from the electrons to the hemoglobin, charging up the hemoglobin, and then allowing the hemoglobin in the blood to deliver that charge to the tissues, which actually, interesting, are called the electron transport chain, which is allegedly where we derive fuel from, which then gives you a perfectly reasonable mechanism of, it's not the oxygen, it's that the oxygen is the carrier of an electronegative charge, which is attracted by the positive charge of the hemoglobin. The hemoglobin picks up this positive charges, changes its configuration, which is what you see. When you test the hemoglobin, you erroneously think it picked up the oxygen because it's now in a charged or different configuration. That doesn't mean it has oxygen, it just means it's in a different configuration, which is a electronegatively charged configuration. The hemoglobin within the red blood cells can then go on to deliver this electronegative charge to the tissues, and you have a perfect mechanism where you actually sync up the need of the tissues for a charge, or sometimes called electrons, with the absorption of these electrons from the world's best electronegative donor in the air as a gas called oxygen. So that's what this next section, does reason exist to entertain such a hypothesis? I don't think I'm going to read all this because I think I just exchanged it. The electron charge could transfer efficiently from the oxygen gas on the alveolar air side to the red blood cells on the vascular side. The Y capillary diameter would need to be smaller. They can therefore be appreciated. The erythrocytes, red blood cells squeeze may be critical for allowing this charge to flow from the oxygen to the abutting red blood cell. And again, Gerald is doing a great job of taking these anomalies like, oh, well, the body made a mistake. It should never have had the capillaries be too small for the red blood cells to efficiently go through, but it turns out there's never is a mistake. This is a perfectly reasonable way to do it. All you have to understand is that you need the red blood cells essentially to squish up against, so to speak, the walls, and that will facilitate the transfer of this charge from the air into the red blood cells. So the proposed cycle would be as follows. The positively charged hemoglobin draws electrons from oxygen, delivers these electrons or charge to the tissues, regaining its positive state and recovering its ability to extract electrons from the inspired oxygen. And actually, we know that hemoglobin has a tendency to easily oxidize, i.e. lose its electrons, so that makes sense. So many things then start lining up when you start thinking about this. So hemoglobin does attract and then delivers the electrons. So we have some good reason to think this may be true. A final consideration involves exhalation. This hypothesis implies at the very least the exhaled gas ought to include what remains of the inspired gas after the electrons are extracted, namely nitrogen and positively charged oxygen. The latter, now with positive charge, should be highly reactive. Hence, the exhaled gas might be expected to contain some product of oxygen and nitrogen, and indeed that's the case. Exhaled gas contains nitric oxide. So now we have another explanation, or a good explanation, for another seemingly unsolvable mystery. Where does the nitric oxide come from? And that's because of the now volatile state of the d-electron or decharged oxygen, which then combines with the nitrogen. And then finally, he says, why are gases such as hydrogen sulfide and carbon monoxide, which are electron donating, so toxic? Shouldn't the proclivity for electron donation make them behave like oxygen? And one possibility is that these gases have the capacity to donate multiple electrons. Oxygen has 5 oxidative states, implying a capacity to donate not just one, but multiple. These gases donate 1 electron, whereas oxygen can donate multiple electrons. So it's essentially the problem, the reason why carbon monoxide is poisonous is that it can only deliver 1 electron or 1 smaller amount of charge as opposed to oxygen. Therefore, you run out of charge, i.e. or electrons, and that becomes a problem, and then your tissues are suffocated and they can't generate energy, and that's why you die. So the noxious gases can only surrender 1, and that's why you can't replace noxious gases for oxygen. And here he talks about the supply and demand, which I talked about, that building adjacent to the cell's hydrophilic surface, easy water largely fills the crowded cell. In doing so, easy water's negative charge arguably accounts for the cell's well-recognized negative electrical potential. So in other words, as I've talked about extensively in the cancer book, we have this, because we have structured water in the cell and it's negatively charged, we have to have a continual replenishment of this electronegative charge, and the electron charge is central, and it's essential for all the functions that have to do with contraction, secretion, nerve conjunction, are all powered by the potential energy of excess electron charge. So the electron charge, or the electronegative charge, is essential to the function of all of our tissue functions. Everything we do is relied on this electronegative charge. Even the fact that the cells don't clump together is because they have this negative halo of charges around them, and you have to keep continually replenishing this electronegative charge. Otherwise, bad things happen and you die. So that's what this gets into. And he says it links the supply and the demand. Electrons are supplied by the respiratory system, And these electrons, or this electronegative charge, consumed by the tissue. This is very simplistic and straightforward, and it all makes sense. So one of the challenges of this I talked about is the oximeter. So aren't you measuring when you put an oximeter on your finger and you say you have so-and-so saturation of oxygen? But Tom, isn't that measuring the oxygen level in the blood? And actually it's not. It's, as he says, the underlying assumption is that the arterial hemoglobin is saturated with oxygen, while venous hemoglobin is devoid of oxygen. Oxygen appears to make the difference. But how would we know if the difference arises from electrons rather than oxygen? The oximeter merely reports structural difference. It says nothing of the basis of those differences. In other words, if the reason the hemoglobin changes is because it's charged or loses its charge, we would see the same thing as if it had oxygen or not oxygen. And so, as he says, we don't know the basis of the difference, and it could just as easily be charged versus uncharged hemoglobin. So you're not actually measuring the oxygen saturation, you're measuring the charge of the hemoglobin, which then makes that a moot argument. So then he gets back as he started. Well, what about these deep sea fish? Oxygen cannot readily diffuse from the atmosphere to depths which these fish flourish several miles beneath the ocean. So how would it be that the oxygen is providing the metabolic energy? Instead, the fish breathe the surrounding water. The water is taken into the mouth. It passes through the gills, exiting through the lateral gills. The exiting water is confirmed to be more acidic, i.e. positively charged, than the neutral intake water. Since the exiting water has gained positive charge, accounting for the water's intake water's neutrality means that the gills must gain negative charge. A mechanism for achieving that charge has been proposed. The gills, like the lungs, are invested with capillaries. These capillaries permit the gills' acquired negative charge to be directly exploited for metabolic needs. Thus, the fish use electrons, electronegative charge from the seawater, in the same way proposed for humans and other vertebrates. So this is not a conundrum. It's a perfectly reasonable thing if you think about the fish need to extract electronegative charge and doesn't need to be from oxygen. Oxygen seems irrelevant for these fish because the oxygen isn't even present. They breathe electrons, not oxygen. And interestingly, he says when they're exposed to oxygen, they die. So they have no capacity to deal with oxygen gas. They must get the electrons from somewhere, and that's from the seawater. And this gets into the next section here, which gets into, so what is this? Is there any use of this for the common person? Can we do anything with this? Does this help us out in any way? So what it's telling us is that we don't actually only need oxygen. It's not to say that we can't use oxygen as the supplier of this electronegative charge. But if we realize that what we're getting from the oxygen is a electronegative charge, then we could think about how to get this electronegative charge from other sources as well as oxygen. Now, again, in the normal situation, it seems to be breathing is fine, and you can get all the electronegative charge you need from the breathing, but from breathing and from supplied by the electronegative capacity of oxygen. But what if you're having breathing problem, or what if you just want to enhance your metabolism? And then you could ask yourself the question, since I know that what I need is this electronegative charge, is there other sources of this electronegative charge which would make it, in a sense, less important that I breathe, and would even enhance my ability to run my tissues, to have my metabolism be healthy and strong, even if there was, say, a deficiency of oxygen, or a deficiency or a problem with breathing, or just in a normal situation. And that leads us into what are some other possible sources that we can use to get an electronegative charge. And here he talks about an interesting story, which I've talked about before, with René Quinton, who was a 19th century French doctor who collected seawater near algae blooms in the Atlantic. And it seemed to be particularly efficacious for helping people with so-called infections and a whole lot of other things. If you go to the Quinton website, you'll find many other conditions which were helped by the consumption, either orally or injected, of Quinton plasma or Quinton seawater. And then I'm going to read this part. Quinton performed a series of audacious experiments even before recognizing the clinical value of this water, and recounted a century later. In early experiments, he infused large amounts of isotonic seawater, up to 104% of body weight, directly into the saphenous veins of dogs, substantially reducing the hemoglobin concentration. The dogs recovered. In a later experiment, Quinton withdrew from the femoral artery essentially all of the dog's blood, about 5% of the body weight, until the animal was fully exsanguinated and at death's door. Only then was the seawater infused over a period of 11 minutes. Following the inevitable functional difficulty, the dog eventually regained full function, notwithstanding substantial diminution of blood hemoglobin. And he says we should repeat these, but this is highly negatively charged seawater or easy water, because the water is sucked out of a continuous vortex. It's essentially the effluent of the microalgae that goes down and is a continuous vortex in the ocean, and the water is sucked out of the center of the vortex, and it's cold, purified, and it's probably the most concentrated source of this electronegative charge. And as these dogs demonstrated, and I've even heard it said that they even use sometimes dogs who had different problems like arthritis or were sick or old or something, and inevitably the dogs, after they had almost all of their blood, of 5% of their body weight, they were basically bled to death, and then they infused back in Quinton plasma, and they were recovered and even better than when they started, which is another way to demonstrate that if you know what you're looking for with breathing and what is it that the hemoglobin, the blood, is carrying, which is not oxygen, but it's this electronegative charge, then you could go out into nature and find probably the two most important sources of this electronegative charge are the connection to the earth, i.e. grounding, i.e. walking barefoot, and then even having your bare feet on the earth and pouring salt water over them, which facilitates the uptake of this electronegative charge from the main electronegative charge donator of all, which is the earth, directly through our feet into our body. And so anybody who's have any issues with breathing or metabolic function or energy should avail themselves of regular, consistent, as much as possible grounding their feet to the earth, because what you're deficient in is this electronegative charge. And probably the best way to get that is through grounding yourself to the earth, and you absorb this electronegative charge, exactly what you get through breathing oxygen through your feet. The second best way that I know of is through availing yourself of ketone plasma, or now, as probably most people know, because I talk about this a lot and I'm going to show it, this is a product that's called marine plasma. We have this on our Dr. Tom Cowan site. And this is made in exactly the same way as the ketone, but it's made by somebody who's really determined to make sure that they're in the best possible location to collect this water and purify it and test it to make sure it's free of any radiation exposure or heavy metals or anything that shouldn't be in there. And it's called marine plasma, which is essentially a modern version of ketone. There's still ketone, and I have no objection to anybody using it, but I happen to think this is the way to go now. And it's something that I've used myself probably for the last 5 years every day. And every morning I keep this in the refrigerator, and I take a full capful and hold that in my mouth for maybe a minute or so. And it seems to be a very efficient way of boosting your exposure to these electronegative charges, because that's what's in this concentrated seawater. And I would encourage everybody who's got any issues with energy or metabolism or breathing problems or asthma or COPD or pulmonary fibrosis to realize that you can, once you understand what it is that you're actually breathing, you're breathing a charge. Therefore, you can get this charge from some other way. It's not that you shouldn't still breathe and still work on helping your lungs, but there is other options, and that will essentially take some of the load off the need to breathe. And my guess is you will find that your life becomes a lot better. Okay, so those are some two very practical, simple, inexpensive ways of applying this new understanding of what it is that we're getting from breathing. It's clearly not oxygen gas. It's something that oxygen donates to us, which seems to be this electronegative charge. And just to finish here, a general implication of the electron-based mechanism is that in biology, electrical charge may reign supreme, i.e. that electrons may be dominant players or charged. These charge could well constitute the common agent of action, not only in the respiratory system, but also in the cellular consumption system, as well as the energy transport systems. That is the new biology. We are charge and water. We are charged and structured water, and we have some minerals and some proteins mixed in there. And all this is geared towards creating the optimal charge, which is essentially a kind of definition of what we mean by healthy. And I outlined this even back as far as the cancer book. If we have no charge, we become a dead battery. The tissues, the cells clump together. We see that as a tumor, and we can link that up to a decreased metabolic function. In other words, the human body may function less as a chemical machine than as an electrical machine. Electrical phenomena are known to dominate numerous aspects of human physiology and beyond, ranging from cardiac electrophysiology to brain function. Here I argue that the respiratory system may function electrically as well. Given the diversity of phenomena acting electrically, it may indeed be appropriate to think of the body as a premier electrical machine. I don't know about the machine word, but I know what he means. And again, it's a very interesting thing. If you ask doctors or scientists, are we primarily electrical beings? They say no. What about EKGs and EEGs and EMGs? And so now we can add that it seems like respiration, just like everything else in us, is primarily an electrical phenomena. And that perfectly jibes with the foundational principles of new biology and our new biology clinic. Okay, so thanks everybody for listening. I know that was probably a lot. Hopefully I was able to explain some of it so it becomes very clear. And thanks again to Geralda Pollacka for doing this amazing research and writing a really well thought out, well put together, brilliant article. So thanks everybody, and I will see you next week.